Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. The course is Statistical Methods 1 with the subject code STP202. In this session, first of all, we are going to deal with random variables, various types of random variables, probability functions of random variables and their properties. We are also going to discuss some of the illustrations of discrete random variable, which is one of the type of random variable. So basically, what is called random variable? In many of the random experiments, sometimes the outcomes are non-numerical, sometimes the outcomes are numerical. If the outcome is numerical, it is well and good, we can proceed further with the numbers. But if the outcome is non-numerical, we can't proceed with the calculations. Hence, these non-numerical quantities must be converted to numerical quantities. So, this kind of transition from non-numerical to numerical is done by the function called random variables. Let me explain the random variables with a kind of an example, how the non-numerical quantity will be converted to a numerical quantity. For example, you consider the experiment concerned with tossing of a coin. If a coin is tossed, all of us know the sample space is head and tail, shortly represented as H and T. These H and T are alphabets and which are non-numerical. Hence, we have to assign a number to this non-numerical outcome of this experiment. We may assign 1 for the outcome head and 0 for the outcome tail. So, it is always possible to associate the outcomes with some real numbers. This kind of association of outcomes with the real numbers is done by the function called random variable. Actually, random variable is a function. Basically, what do you know about a function? The function, for example, you may call f of x is equal to x square. This is a very common function, all of us know. So, what has been done here is a point x in the domain A is being converted as the point x square in the range B through a transition called f. Okay. So, that is why we represent it as f of x is equal to x square. Okay. So, similarly, I am going to take a sample space with the outcomes h and tail, and we have given the association 1 for the head and we have given the association 0 for tail. This is done by the random variable x, which is actually a function. Okay. So, this 1 and 0 is the range space of x. So, actually the random variable x is a function from the domain S to Rx. Rx is a range space of x. So, coming to the mathematical definition of random variable, let E be a random experiment and S be a sample space associated with the experiment. A function x assigning to each element s belonging to s a real number is called the random variable. So, example of random variables. The simple example I have already explained before explaining the random variable. Now, the formal example of random variables is, consider the experiment of tossing a coin twice or 2 coins tossed at a time. The samples points of this experiment are head on both the coins, head on one coin, tail on another coin, and similarly tail on first coin and head on another coin and tail on both the coins. These are the 4 sample points. You have to define the random variable x for each and every experiment. Okay, the x be the number of heads. So number of heads means possibly with 2 coins you can at most have 2 heads, isn't it? So the random variable takes the possible values as 2, 1, 0. These are the 3 values which a random variable is taking here for this example. So based on numbers which the random variable assumes, there are 2 types of random variables. What are the 2 types of random variables? We know the numbers may be discrete or continuous. So based on the numbers, we have 2 types of random variables. One is discrete random variable, another one is continuous random variable. So what is meant by discrete random variable? If a random variable is said to be discrete if it assumes only a finite or countably infinite values of x. The range space x Rx contains a finite or countably infinite points. Okay. Example of discrete random variable, you consider the experiment of tossing the die. The sample points are obviously 1 point on the die or 2 points on another face of the die, 3 points on another face, likewise 4, 5, 6. Here the sample space are numerical. Hence the random variable assigning is also very easy. You can say the points on the die. Then obviously random variable takes the values 1, 2, 3, 4, 5, 6, which is here finite and as well as countable. You are able to count 1, the next number you are able to count it as 2, 3, 4. So it is finite as well as countable. So based on the assumption of the values of the random variable x, we call this is a discrete random variable. Another example of discrete random variable is number of telephone calls per unit time. Okay, you can count how many calls are coming in a unit of time. For example, in 1 hour you can just count 1 call or 2 calls or 3 calls, like that you can count the n calls in a unit of time. So that is also a discrete random variable. Even if it is infinite and if you are able to count, that random variable is called as discrete random variable. And almost another example is number of successes in trials. We have discussed the discrete nature of a random variable where it can be infinite but it should be countable. Okay. What happens to a number which takes the values in an interval? In an interval, for example, if you consider the interval 1, 3, by looking intuitively you can say how many numbers are there in this interval? 1, 2, 3, isn't it? It is not like that. There are uncountable values in the interval 1 to 3. For example, if I take the point 1.11, it also belongs to the set 1, 3. And if I take 1.111111 etc., that also belongs to the set 1, 3. Okay, but it means that you are not able to count and you cannot predict how many numbers are there in the interval 1, 3. So if you are not able to count, that becomes uncountable points. That is called continuous numbers. If the random variable assumes such type of numbers, then it is called continuous random variable. Okay. So a random variable is said to be continuous if it assumes all the possible values. That's what it's called, all possible values, like 1.11111. If you can put this 1 etc. up to infinity, then also it belongs to the interval. So all the possible values in an interval, then it is called continuous random variable. Example of continuous random variable is exactly measure the height. You can say the height varies from 15 centimeters to 16 centimeters, like that. So weight also, it is a variable, it is varying, it is continuous. So these kind of factors, height, weight, age etc. are continuous in nature. So these kind of kind of continuous nature parameters are called continuous random variables. Okay. So based on the discrete and continuous nature of the random variable, the probability functions also will be defined. Okay. We define probability mass function for discrete random variable and probability density function for continuous random variable. Probability mass function shortly called as PMF, okay, and probability density function shortly called as PDF. First of all, let us see the definition of probability mass function. Let x1, x2, x3 be possible values of a discrete random variable x. When you are defining the values of discrete random variable, you must write in this way only, comma x1, comma x2, comma x3, like that. You can't define the values in an interval, then it becomes continuous. Okay. So x1, x2, x3, etc. are the possible values of a discrete random variable x. Then P of xi is called probability mass function of the discrete random variable x if the following conditions are satisfied. Basically, probability mass function is a function of the probability. So the probability conditions should be satisfied for the function of the probability also. Okay, what is the first condition? All the probability values should be greater than or equal to 0 for all the possible values of the discrete random variable, because probability values are always lies between 0 to 1. So it should be non-negative. That is why it's called P of xi is greater than or equal to 0. And the second condition is total probability. P of xi is equal to 1. Summation P of xi is equal to 1, where I ranges from 1 to infinity. So this second condition mentions totality of all the probability values is equal to 1. That is, total probability is 1. Next definition, probability density function. Let x be a continuous random variable. We have defined probability mass function for discrete random variable, and now we are going to define the probability function for continuous random variable. As I already told you, what is meant by continuous random variable? It is the random variable which takes the values, all the possible values in an interval. Okay. So let x be a continuous random variable means it is taking all the values in an interval. Then f of x is called probability density function PDF if the following conditions are satisfied. The first condition is again f of x defines a probability, mentions a probability, so it should be greater than or equal to 0 for all x belonging to the capital X. This capital X is going to be an interval because it is continuous. Okay. The second condition is the total probability is equal to 1. Total probability here for continuous, we have to use the notation integration for continuous. If it is discrete and countable, finite, you can add. If it is continuous and uncountable, you have to definitely integrate. Okay. So integrating minus infinity to plus infinity, f of x dx is equal to 1. Okay, this is the second condition which mentions total probability is equal to 1. Let us now have a short break. Welcome back after the break. Before the break, we have seen the random variables and types of random variables based on the nature of the numbers that is random variables assumes, that is discrete random variable and continuous random variable. For the two types of random variables, we have seen the probability functions, probability mass function and then probability density function. Okay. Now let us proceed further with the probability density function. So probability density function definition has been defined as cumulative distribution function. Let x be a discrete. This cumulative distribution function, it can be defined for both the random variables, discrete or continuous. So hence we can take x be a discrete or continuous random variable. Then the function f of x is equal to p of x less than or equal to x. That is what is called cumulative. Cumulative means from the beginning till now, it is called cumulative. adding all the parameters from the beginning till now, it's called cumulative. So is equal to p of x less than or equal to x is called cumulative distribution function of the random variable. If x is discrete random variable, then we define the cumulative distribution function CDF as f of x is equal to p of x less than or equal to x. Since it is a summation, we have to use the summation sign addition, where xi is taking all the values which is less than or equal to this particular number x and p of xi. Okay. So for discrete random variable, you have to use the summation because it is discrete, countable and finite sometimes. If x is a continuous random variable, then f of x, the cumulative distribution function, is defined same p of x less than or equal to x. It is equal to, we have to use integration. It is being integrated from the limit minus infinity to x, f of x dx. Okay. This is the basic definition for cumulative distribution function defined for discrete and continuous random variable. Let us see some of the properties of a cumulative distribution function. First property is f of minus infinity is equal to 0, f of infinity is equal to 1, f of x is non-decreasing function. If a is less than b, then p of a less than x less than or equal to b is equal to f of b minus f of a. If x is a continuous random variable with PDF f of x, then capital F dash of x is equal to f of x. This fourth property actually gives the relationship between PDF and CDF. PDF is probability density function and CDF is cumulative distribution function. We will see the proof of these four properties one by one. The first property is, we have to prove f of minus infinity is equal to 0 and f of infinity is equal to 1. Let me take the x as this continuous random variable itself, then I will prove the proof. Okay. So first of all, how capital F of x is defined for continuous random variable? It is defined as p of x less than or equal to x is equal to minus infinity to x f of x dx. So in the place of small x, if I put minus infinity, then I have to use the integration as minus infinity to minus infinity f of x dx. An integration from the same point to the same point is not possible in continuous, because continuous means it has to take the values in an interval. So this is not possible, therefore minus infinity to minus infinity, the value is 0. Coming to the next one, to prove f of infinity is 1, again use the definition f of x is equal to p of x less than or equal to x minus infinity to x. So in the place of x, I am going to put it as plus infinity f of x dx. Have you seen this terminology anywhere? Minus infinity to infinity f of x dx. Yes, it is the second condition for which the probability density function should satisfy. So minus infinity to infinity f of x dx should be definitely equal to 1 because it represents the total probability. Property 2, we have to prove f of x is non-decreasing function. That is, we have to prove if x1 is less than x2, then f of x1 is less than f of x2. Okay. So in general, I will take xj minus 1 if is less than xj, then to prove f of xj minus 1 is less than f of xj. Okay. So first of all, what is f of xj minus 1 stands for? F of xj minus 1 is nothing but p of x less than or equal to xj minus 1. Okay. So it represents the summation I is equal to 1 to j minus 1 p of xi, that is this is equal to P of x1 plus P of x2 plus etc. up to P of xj minus 1. Okay. Similarly, I take f of xj. F of xj is P of x less than or equal to xj. This is equal to summation I is equal to 1 to j P of xi. Okay. So, this is equal to P of x1 plus P of x2 plus etc. P of xj minus 1 plus P of xj. Okay. So, comparing this 1 and 2, what do you have? F of xj minus f of xj minus 1 is equal to, when you subtract, P of x1 minus P of x1 gets cancelled and P of x2 minus P of x2 gets cancelled, up to P of xj minus 1 to P of xj minus 1 it is getting cancelled, and you have only P of xj. Okay, P of xj, which is a probability of a sample point xj. This is obviously greater than or equal to 0 by the property of probability mass function. Okay. So, automatically we have f of xj is greater than or equal to f of xj minus 1. Hence, f of xj minus 1 is obviously less than or equal to f of xj. This is how we have proved f of x is a non-decreasing function. Let us see property number 3. Property number 3 says, if a is less than b, then p of a less than x less than or equal to b is equal to f of b minus f of a. What is that? We have to prove probability of x taking the value between a and b is equal to f of b minus f of a. Let me draw the axis. Suppose if you take the point a here and take the point b, because a is less than b, you can have to take like a first and then b. Okay. So, x less than or equal to a. Let me take x less than or equal to a represents this up to minus infinity. X less than or equal to a. Take the 3 events, x less than or equal to a, and this particular place a less than x less than or equal to b. Okay. So, this slanting lines and this particular part, when you add, what do you get? You get x less than or equal to b, right. So, mentioning this in terms of probability, p of x less than or equal to a plus p of a less than x less than or equal to b ultimately gives you p of x less than or equal to b. Okay. According to the definition of cumulative distribution function, p of x less than or equal to a represents f of a, and I keep this as it is p of a less than x less than or equal to b, and p of x less than or equal to b again according to the definition of cumulative distribution function represents f of b. So, ultimately you have p of a less than x less than or equal to b is equal to f of b minus f of a. Hence, proved. Clear? Then going to property number 4. If x is a continuous random variable with PDF f of x, then capital F dash of x is equal to f of x. This is a relation between CDF and PDF. Coming to the original definition of CDF, cumulative distribution function, we have defined f of x is equal to p of x less than or equal to x. In the case of continuous random variable, we have defined minus infinity to x f of x dx, isn't it? So, in the integration and differentiation are opposite to each other. when you differentiate f dash of x, you get small f of x. That's it. So, if x is a continuous random variable with PDF f of x, then f dash of x is equal to f of x. Now, summarizing what we have seen in this session, we have seen what is meant by random variable. Actually, random variable is a function which converts the non-numerical quantities to numerical quantity, that is assigning the outcomes of the sample space with the numbers to proceed further. Okay? Based on the real numbers nature, we as discrete and continuous, there are two types of random variables, discrete random variable and continuous random variable. Hence, we have defined about the random variables and its types. Then we have to talk about their probability functions. Probability functions are also defined as two based on the random variables types. That is, probability function for discrete random variable is defined as probability mass function satisfying two conditions, p of xi is greater than or equal to 0 and total probability summation p of xi is equal to 1. This is probability mass function for discrete random variable. And probability function for continuous random variable is defined as probability density function, okay, which satisfies two conditions again, f of x is greater than or equal to 0 and minus infinity to infinity f of x dx equal to 1. Okay. So, we are after defining the probability functions for both the discrete random variables, both discrete and continuous random variables respectively, we have to define the cumulative distribution functions for both the random variables, discrete and continuous, which is capital F of x is equal to p of x less than or equal to x. It is being defined as summation for discrete and which is defined as integration for continuous. And we have discussed some of the properties of distribution function, cumulative distribution function, CDF. Property 1 is f of minus infinity is 0, f of infinity is 1. Second property is f of x is non-decreasing function. Third property is if a is less than b, then probability of x taking the values between a and b is equal to the difference in the CDFs, respective CDFs. Then property 4 defines the relationship between CDF and PDF. Capital F dash of x, differentiation of CDF is equal to the actual PDF f of x. Thank you.